Okay, guys, welcome. Today we're going to talk about coloring graphs with two colors. Now, for the motivation behind this idea, we're going to suppose that Jim has 6 children and that their names, again, for alphabetical convenience, are Al, Bob, Chris, Di, Eve, and Faye, right? Now, the children have a tendency to fight. We know that Chris fights with Bob, Faye, and Eve. Eve also fights with Al and Di, and then that Al and Bob fight. Now, Jim wants to put the children in 2 rooms so that the pairs of fighters are in different rooms. We want to know, is this possible? And of course, this is much easier to use a graph. All right. Now we're going to construct a so-called fighting graph by representing each child with a node and connect the nodes if they fight, right? So here we have that Alice, Al, and Bob fight, and Al and Eve fight. Eve also fights with Diane. I think this was Carl, right? Chris. And then Bob and Chris fight, and then Faye and Chris fight. Right? Now, one solution is to pair A, C, and D, I'll just use the letters now, on one side and put them in one room, right? None of them fight with each other. And put B, F, and E in the other room. And of course, none of them fight with each other, right? So that's one way to do it. Now, instead of rearranging the nodes with left and right sides, we could have just colored the nodes black and white to represent the room they go to, right? Now, the rule of coloring for graphs is that adjacent nodes must be colored with different colors. So a graph might look something like this, right? So all of the solid nodes would go to one room. So we'll say room 1. And then the hollow ones would be in the second one. Right? And of course, we're showing the same information. Now, the rearranged graph was a bipartite graph, while this colored map, this one right here, is what we say is two colorable, because we were able to color it with 2 different colors and no adjacent nodes have the same color. Right? And of course, they represent the same information. So now, in terms of this idea of coloring, the question then becomes, which graphs are 2 colorable? Okay, now let's think about this for a second. If a graph has isolated nodes with no edges, one color will do the job because there's no edges, so there's no such thing as adjacent, so one color is fine. Now, if a graph has at least one edge, then you need at least 2 colors, because if you just have 2 nodes connected by a single edge, then you at least need to make these 2 different color, right? And that's regardless of what's going on in the rest of the graph. If you have a triangle or a graph containing a triangle, then you would need 3 colors, because then you have this situation. Now, of course, that other node cannot be hollow or solid, so I need to make it a different color. Let's just say use orange here, and we'd have something like that. Okay, now what about a pentagon? If we try 2 colors, you end up with colors that are next to each other, right? So if you start with V1, making that hollow, then go to V2, which is solid, V3, hollow, V4, solid, then you have no choice for V5 but to make it hollow, but then that's going to be a problem because it's going to be right next to another hollow one. Now, of course, this is going to happen with any odd cycle, right? So a graph is 2 colorable if and only if it contains no odd cycle. So the idea in the textbook is to use the same sort of principle as this, but I'm not going to draw it out here just for time's sake, right? And again, the general idea is to pick a node, color the neighbors the opposite color, and repeat, and you just keep doing this. All right, so that's for graphs with 2 colors. Now, if we want to use many colors, of course, for the scenario that a graph is not 2 colorable, but it could be colored with more. Now, if there are n nodes, you could use n colors, and of course that would do the job, but the idea is that we may want to do better than that, right? We may want to use the least amount of colors as possible. So if we can color a graph with k colors, we'll say that the graph is k-colorable, and the smallest such k for which a graph is k-colorable is what we call the chromatic number. of the graph. Okay. Now it's much more difficult to jump from determining if a graph is two-colorable to three-colorable. And one known result is called Brooks' theorem. If every node in a graph has degree at most d, then the graph can be colored with d plus 1 colors, right? Now, of course, just note that it's possible to have a graph with some nodes having high degree and the graph is two-colorable, right? So this is what we say may be a sufficient but not necessary condition, right? Because it is possible to have a graph with nodes having high degree and the graph being just two-colorable. Now, the proof that we do is by induction, right? So for the base case, right, if it's degree at most 1, then we saw, for example, that the graph can be colored with d plus 1 colors, right? So the base case is simple. Okay. Now, for a graph with less than d plus 1 vertices, it can be colored by d plus 1 or fewer colors by using a different color for each vertex. So that's one idea. Now, suppose our theorem is true for any graph with fewer than n vertices. Okay. Now, pick a point V of your graph G and omit V and its attached edges to attain a graph G prime. Now, G prime has n minus 1 vertices, so you've taken one vertex away, and every degree is still at most d, right? So you don't change the degree, right? If you pick a point and you remove its attached edges, right? Well, I should say you don't add a degree. So G prime can be colored by d plus 1 colors. Now, since V has at most d neighbors, but we have d plus 1 colors, there must be a color that does not occur among the neighbors of V. So then color V with that color, and that gives the coloring of G by d plus 1 colors. Okay, so that concludes this video on coloring in graphs. I hope you enjoyed, and I will see you next time.